and we're gonna have some fun. Oh, there is no maybe. It's time for quiz 10. Yeah. Okay, now, what's quiz 10 about? Quiz 10 is fun because what we're going to be talking about is the question whether we can have this infinite sum, a series, if something converges or something diverges. And so our basic things that we've learned this week, and so these should be our default things to go to. We'll just make a quick list here on the side. So we have the 4 ideas we should be thinking about. Comparison, limit comparison, which is like comparison, but taking it to the limit. And then we have the ratio test, and we have the root test. So we're going to be talking about using these 4, and the question is converge versus diverge. And so it's almost like yes or no. So even if we just guess at the start, we've got a 50-50. Now, of course, we want to get better than that. We don't just want to have to say, I think it's going to converge, or I don't. Oftentimes, we want to know the answer before we even start working. And oftentimes, we can. All right, so let's do it. 10 problems. Here we go. Number 1. Determine whether the sum from 1 to infinity over 1 n to the half plus n to the 3 halves converges. Now, what do we do? Well, we could, of course, make our life miserable and do an integral test on this. It's not impossible, but not desirable. So, why? Well, because we have better tools. Now, let's look at our 2 terms downstairs, because we see this plus. That plus really says, hey, I have 2 pieces. And whenever you have more than 1 piece, your goal is to say, which piece is important? Which piece is controlling the behavior? What's the one part that rules them all? One term to rule them all. One term to find them. One term to bring them all, and in the light of calculus, bind them. So, which one's bigger? And the reason I ask which one's bigger is I want to know which one's controlling the growth. N to the half, n to the 3 halves. The answer is n to the 3 halves is bigger. So I say, all right, that's what's controlling the growth. Good. Well, now that I know what's controlling the growth, I say to myself, okay, suppose it was just n to the 3 halves, so we were ignoring that for a second. Would that converge? And how do we know? Well, okay, does it converge? Yes. How do we know? Well, what kind of sum is it? It's a p-series. It's a p-series where p is 3 halves, and therefore it converges. So we now know the answer to this question. Does it converge? Yes, it converges. Well, all right, but we got to justify that, right? Yeah, of course we have to justify. We want to get credit. It's not like this is a multiple choice problem. No, we got to explain why. So it converges, and our key is we want to compare it somehow to say, get rid of the n to the 1 half. So this is probably more of a limit comparison or comparison type problem. And all right, so what do we use? Well, if we were going to do a comparison, what would we want? We want to compare it, and if we want to show this converges, we want to get it below something which converges. So the question is, what can I put here? Well, the key is, remember, if I want to have a larger number, smaller denominator. So if I get rid of a term, that's going to be a smaller denominator, so a larger number. So this is below 1 over n to the 3 halves. And of course, these terms are going to be greater than or equal to 0. And since we know that the sum from 1 to infinity of 1 over n to the 3 halves converges, and why? Well, we already said it, but we're going to write it down. It's a p-series. So, by comparison test, then the original sum converges. And we're done. Now, we should comment here, we were really clear from the start what we wanted to compare it to. Because we could have said at the same time, we could have said, and this would have been silly to do it, but okay, let's do our silly thing in a different color. We could have said, hey, look, 1 over n to the half plus n to the 3 halves is also below 1 over n to the half. 100% true. There's the true truth there. Okay, so why didn't we use that? Well, look at the sum of 1 over n to the half. Does that converge or diverge? Well, it's a p-series, but this time it's a p-series which diverges. And if I have something below diverging, then I get to make no conclusion. So this is useless. So we're not going to do that. All right, so that's number 1, converges. All right. Well, number 2. Determine whether the sum from 1 to infinity of 1 over 2 to the n minus root n converges. So again, we see that minus. It's really like a plus, but it's a pessimistic plus. So between 2 to the n and root n, which one is the more important term? In other words, which one is really going to describe how it's going to grow? Well, the answer is root n behaves polynomially in some sense. It's the power of n. 2 to the n, that's exponential. And exponential beats things which are polynomial. So that's controlling our growth. Okay, so now that we have that, what's going to happen? Well, that says that really ignore the root n and ask about that sum. All right, so take the sum 1 over 2 to the n. Does it converge or does it diverge? And the answer is, well, it converges. Why? Because 1 over 2 to the n, what kind of sum is it? It's geometric. It's a geometric sum which converges. All right, good. So we have an idea. Now, can we do the same thing? Well, if it converges, we could try the same thing, right? We want to get this below something which converges. Now, last time we just said, haha, cover up the root n and life is good. This time, is this true? That 1 over 2 to the n minus root n is less than or equal to 1 over 2 to the n. And it is not true. The problem here is 2 to the n minus root n, smaller denominator, and therefore this is actually the larger number. Okay, good. Now, can we salvage it? Yes. Is it easy? No. No. It's hard work. Hard work. So, well, what can we do? Well, anytime we have a comparison test, we can almost always use a limit comparison. In some sense, limit comparison is the better test. So, how do we do limit comparison? Well, what we say is we'll do a limit comparison. If we think of this as our a sub n, then we let b sub n be the parts which have the biggest pieces. So 1 over 2 to the n. In essence, we're throwing out the small stuff. And I think there was a book, right? Don't worry about the small stuff. And then the subtitle was, and it's all small stuff. All right, good. So what happens? Well, we want to take a limit as n goes to infinity of an over bn. So that's our limit. N tends to infinity of 1 over 2 to the n minus root n. Divide that by 1 over 2 to the n. Now, you clean that up, and you see that this is limit as n goes to infinity of 2 to the n over 2 to the n minus root n. But really what's happening here is you say, let's divide out by that largest term on both top and bottom. And the largest terms will be the same. We've designed it to be the same. So this is really the same as the limit as n goes to infinity of 1 over 1 minus root n over 2 to the n. And now, aha, this term This term right there. See, polynomial over exponential. Exponential always wins that race. So the limit is 1. Now, if you're not careful, you might say, 1? Oh, no, that's terrible. But wait a second. Got to remember what test you're in. What does the limit comparison test say? It says, as long as you get some number here, any number from 0 to infinity, just some number, that's all we need, then life is good. And in particular, what we can conclude is we can say, well, look, the sum from n equals 1 to infinity of 1 over 2 to the n minus root n converges if and only if, and the only bad part about this is you have to write out the phrase if and only if. Mathematicians, by the way, have a shorthand. They call this the if. So if you ever see the IFF, it's not a typo. Well, it might be a typo, but oftentimes it means if and only if the sum n equals 1 to infinity of 1 over 2 to the n converges. Okay, now, does this sum converges? And this sum converges. Why? Well, we said it before. And I know it feels like a broken record, but the reason we need to do this is we need to justify. And it's because this sum is geometric. So there we go. So it's not kind of, you're going to get used to this kind of a rhythm wherein we're like, hey, here's sort of, yes or no. Does this converge or not? And we're able to say yes, and then we have to say, okay, why? Well, then we go through the details. So oftentimes, let's put our answer up here, converges. Oftentimes we're going to know the answer before we even start the problem, which is kind of fun, because then, it makes it really easy on us. We know. Okay. Number 3, determine whether the sum from 1 to infinity 5n cubed plus 3 root n over 2n minus 17 converges. Oh my gosh. Well, what is this? It's a lot of noise. So let's peer through the noise. And the way we do that is we say, okay, how is the numerator behaving? In other words, what's the rate of growth of the numerator? Well, the top, it's essentially it's polynomial. This is powers of n, right? N to the half, n cubed. So, all right, so it grows like polynomial. What's the highest power? So, the growth here, the numerator, it's acting like n cubed. Downstairs, what's it acting like? Well, it's acting like n. So, that says that the terms are growing roughly like n squared. Now, we think to ourselves, okay, well, what's true about the sum from 1 to infinity of n squared? So this is sort of our reasoning. So what does this sum do? Is it converging or is it diverging? It does look like a p-series, right? And so this sum, it diverges. Now you might think, wait a second, what about p? Well, you got to be careful here, because if we were trying to, like we normally write a p-series, normally it would be n to the minus 2. And you'll see that minus 2 is certainly less than or equal to 1. Okay, but actually there's an even simpler reason why this diverges. Do you see what's wrong with this sum? If you start adding up n squared, so you get like 1, next time you get 4, and then 9, then 16, then 25. The terms are getting bigger and bigger and bigger. So these terms get arbitrarily big. Well, you can't converge if they get arbitrarily big, right? In fact, we can use a little simpler test. We can say, hey, let's look at how the terms are growing. So let's look at the limit as n goes to infinity of our a sub n. So the limit as n goes to infinity of 5n cubed plus 3 root n over 2n minus 17. Well, let's see what we can say. So the growth is faster on the top than on the bottom. Well, what's the smaller growth? And the answer is downstairs, it's growing smaller. So we're going to divide out by that growth. So 1 over n. So this is the limit as n goes to infinity. And downstairs, 2 minus 17 over n. And upstairs we get 5n squared plus, well, 3 times 1 over root n. And what happens? Well, downstairs you get a 2. And that's sort of the nice thing is when you divide out by growth, you're going to get something finite to play with. And upstairs it's getting huge. So it's going to get arbitrarily big. Now what this says is that the terms in the sequence get arbitrarily large. So if the terms are getting arbitrarily large, what does that say about our series? It's the nth term test. And we have that the limit of the nth term goes often arbitrarily big. And so since, in particular, it turns out, true fact, infinity and 0 are not the same, the sum has to diverge. Now we could have also done a comparison test with, say, n squared, but one of the nice things, and from a mathematical perspective, this is actually a fun fact. From a student perspective, this sounds miserable, but what you can do is oftentimes you get more than one test that can work. And so you can use the different tests to answer different things, do it different ways. So, okay, number 4. Ooh, this looks really familiar. It's almost the same as the last one, right? In fact, if you were to compare the two, they look almost identical except for one little teeny tiny thing right there. That's the only difference. Well, how much of a change could that lead to? As they say. All right, so let's think about this. So again, let's try to answer this before we get too far along in our process. So let's think about this here as our a sub n. And whenever you see things like plus or minus, really the long-term goal is to ask the question, what's the growth? And in other words, limit comparison says, get rid of all that noise, just think about the growth. All right, so let's do that. Okay, so on the top, it grows like n cubed. That's the highest power on the top. And the downstairs grows like n to the 5th, so you end up with 1 over n squared. Now, this is going to be our b sub n. All right, so the question, what happens to the sum of 1 over n squared? Does it converge or does it diverge? Well, sum of 1 over n squared is going to converge, right? Because it's a p-series. And we know about p-series. So our answer is going to be converge. Now we need to justify it. We sort of did a quick sketch of justification. We know why. Now we're going to repeat it all but write it down. So our justification was, we said, look, these two series are going to be tied together because we're really doing a limit comparison. So we're going to take a look at the limit as n goes to infinity of a sub n over b sub n. So that's the limit as n goes to infinity. So a sub n, well, I'll just write it down. That's 5n cubed plus 3 root n divided by 2n to the 5th minus 17. Now I'm going to divide it by b sub n. So I'm going to think of b sub n in this first form we wrote down. N cubed over n to the 5th. Now dividing it by b sub n, all right, so if we divide this by b sub n, it's the same as, and this is going to sound a little bit strange, multiplying by, on the top, 1 over n cubed, and on the bottom, 1 over n to the 5th. So what's happening is I'm taking the reciprocal of b sub n by taking the reciprocal of the top and the reciprocal of the bottom. And it's absolutely true, if I take the reciprocal of the top and the reciprocal of the bottom, then the whole net effect is it's the reciprocal of what I want it to do. So this is the limit as n goes to infinity. On the top, 5 plus 3, and then we're going to have square root of n over n cubed. I'll just write that as n to the minus 2.5. Downstairs we're going to get 2 minus 17n to the minus 5. Okay, and then what happens as we go to minus infinity? As we go to infinity. Sorry, the minus is in the exponent. Okay, all right. So, n to a negative power, so a large number to a negative power gets very small. Very small. So, that's going to get small. That's going to get small. So what are we left with? We're left with 5 halves. Now, what do we care about this number? The answer is not much. What we care about is that this is a number. Oh, that's good news. Yeah. See, what we care about, this is some number between 0 and infinity. We really just want to make sure it converges to something. And so, since it does, we're good. All right. Good. So what does that tell us? So, by the limit comparison test, and now comes the long explanation here, since the limit as n goes to infinity of an over bn equals 5 halves, then the original sum will converge, and so here we go. It takes a while to write this down, right? If and only if, the sum 1 to infinity of 1 over n squared converges. But, what do we know? The sum, n equals 1 to infinity 1 over n squared, is a p-series which does converge. And that's good because we're out of space, right? We really are really out of space there. So the limit comparison test really says, hey, throw out all that unnecessary noise and focus on just the growth. Does that converge? And if the answer is yes, then the original sum converges. If the answer is no, then the answer is no on the original sum as well. And so we see, we get convergence, and so our original sum converges, and life is good. Woohoo! Life is good. All right. Now, number 5. Well, determine whether the sum 1 to infinity, the square root of n squared plus 1, sine squared of 1 over n, converges. And I think it's safe to say that compared to the previous problems, our first reactions when we see something like this is, it's not so clear. It's a little different. In fact, I think that's understating it. It seems a lot different than what we've been talking about so far. So, how do we approach this? Okay, so let's pause for a second and let's think about what's happening here. Our philosophy, when we're looking at whether things converge or diverge, often boils down to asking a very basic question. What can we say about how things are growing? And if we can understand how things grow, then we're okay. So let's think about our pieces here. Square root of n squared plus 1. Well, what is that like? Well, notice that the plus 1 really doesn't have a big effect. So it's basically like the square root of n squared. And of course n here is positive, so it's like n. So this first term is growing like n. All right, how about sine squared of 1 over n? All right, now here's something interesting. Let's talk about sine for a second. So this is kind of a neat little fact, and it's one of those little facts which you kind of know it, but you may not realize that you know it. So let's suppose this is our function sine of x. Now, if you were to look at sine of x, and you were to look at 0 and ask what's the tangent line, well, you get something like that. And if you were to zoom in, because Well, that's often times how we do things in math, is say, what happens if we zoom in? Well, what would happen is that you'd get your tangent line, which is this line, y equals x, and then you'd see that sine of x would come in and be almost right on top of it. Okay, so there's our sine x. Now, what's the point here? Here's the fun fact. And once you realize this, it really helps you see what's happening on this problem. And it's for x near 0, sine of x is about x. And really that's all that's saying, and it sounds like it's a very complicated fact, but all that's actually being said right here is that the function approximates its tangent line when we're near the point of tangency. Okay, so let's get back to our regularly scheduled problem. Sine squared of 1 over n. See, 1 over n, that's near 0. Especially because I really care about when I'm huge, I'm near infinity. So this is approximately, well, 1 over n squared, or 1 over n squared. So what that says is that for n large, we have the square root of n squared plus 1, sine squared of 1 over n is approximately, this term here is about n, this term is about 1 over n squared, and if you multiply them together, you get 1 over n. Okay, so now it's starting to come into focus. So what's our key here? Well, these terms are going to behave like 1 over n. And we're going to justify all of that in a few minutes. But suppose now, I didn't ask you about this sum. What do we know about the sum of the approximation? Sum 1 to infinity of 1 over n. What can we say about that? Does this converge or diverge? And why does it diverge? So, okay, first question, does this converge or diverge? The answer is, it diverges. Good. Aha, I thought you might get that one. Do you remember why? Yeah, you're right, it's a p-series, but what else is it? It's harmonic. This is the harmonic sum. Okay, so we now can say that we think the answer is diverge. So we're going to write diverges up here, but now let's finish it. So our we're like, okay, we're kind of see where this is going. This will be our a sub n, and now this will be our b sub n. So we're going to take a look at the limit as n goes to infinity of our a sub n, divide that by b sub n. So that's going to be the, limit. Yep, see, you can't even tell I made a mistake there. Ha, it's so natural. All right, square root n squared plus 1 sine squared 1 over n, divide that by 1 over n. Now, what are we going to do? Well, there's another nice fact we have, and wow, this is a great stroll down memory lane. There's something else. Do you remember this following fact? Sine of blah divided by blah goes to 1. As long as what? As blah goes to 0. Okay, so notice how we have sine of 1 over n. There's another 1 over n. What we'd really like here is to get another 1 over n. Now where are we going to find another 1 over n? Well, good news, we have something. See the top? Let's go ahead and pull out an n squared from that first term. So this is the limit as n goes to infinity. If I pull out an n from that first term, that would become n square root 1 plus 1 over n squared times sine squared of 1 over n divided by 1 over n. Now this n goes down. And when it comes downstairs, it becomes downstairs as what? Well, as if it's n upstairs, to come downstairs, it'll have to flip over. So it's going to come down as a 1 over n squared. So we have the limit as n goes to infinity square root 1 plus 1 over n squared. And then I'm going to go ahead and, since all these terms are squared here, sine of 1 over n divided by 1 over n. Now, take the limit. The first term here does what? Square root of 1 plus 1 over n squared? It goes to 1. Second term, it's the sine of blah over blah, right? 1 over n. 1 over n goes to 1. Sorry, 1 over n goes to 0. So this term goes to 1. And then you square it. So our limit is 1. Done. Good. Well, not quite. We need to write a few more things. So, by limit comparison test, because we always want to say what test we're using, since this sum, 1 to infinity, of Bn diverges, now you could have said just Bn, or you can write 1 over n, then the sum 1 to infinity An also diverges. This is a way to save a little bit if you don't want to rewrite the whole sum all over. Cool. All right, and that's number 5. That means we're halfway through. Woohoo! Cool. Good stuff. Good stuff. All right. Number 6. Now, determine whether the sum 0 to infinity of 2n plus 3n over 3n plus 4 to the n converges. Now we're looking at this and we're thinking, ooh, this looks geometric. Now, is it geometric? No. What screws it up? The thing that screws it up from being geometric is this plus sign downstairs. Crazy plus sign downstairs. You're ruining it for the rest of us. If you weren't there, we could just actually find the exact value. Grrr. Okay, all right, so it's not just geometric. But it kind of behaves like geometric, right? Now you might be thinking, root test, because everything has nth powers, but you don't want to use a root test here. And why not? Because of these plus signs. Plus signs, ruin it yet again. Okay. Well, don't worry. Remember, we have ways to deal with plus signs. And sort of the default way to deal with plus signs is limit comparison test. But before we do that, let's make up our mind. Does this converge or diverge? So, on the top, which one's controlling the growth? Which one's growing faster? 2 to the n or 3 to the n? It's the 3 to the n, right? Bigger growth. How about downstairs? Which one's faster? 3 to the n or 4 to the n? Well, it's the 4 to the n. It's, bigger growth. So really, for very large values, it looks like 3 to the n over 4 to the n, or 3/4 to the n. Now, if I add 3/4 to the n, does that converge or diverge? And why does it converge? Okay, so let's go to the first question. Does it converge or diverge? Yes. It converges. Okay, good. Why? What kind of sum is it? It's geometric. It's geometric where our R value, the thing we multiply every stage, is 3/4. Okay. Now we have to justify it. We could do limit comparison, and that could work, but let's see if we can make it work with just comparison. We should try a little bit with comparison, because comparison is kind of feeling left out. We've done so much with limit comparison today. Okay, so if we think it converges, well, are all the terms greater than or equal to 0? And that's easy to say yes. Yes, it is. No problem. Now, that says we need this to be less than or equal to something which converges. Okay, so our rule of thumb is we want to make sure we get a smaller denominator, because if it's a smaller denominator, it's a larger number. And we need to get a larger numerator. So if I have an expression and I want to find something bigger than it, I say I want to make the numerator larger and I want to make the denominator smaller. Now, oftentimes making things smaller or larger can be pretty easy if we throw things away. So there's two things we can do. In fact, we're going to do both of them in this case here. So first off, how do you make something smaller? Well, the thing is, you say, okay, let's throw away the piece that's less important. So between 3 to the n and 4 to the n, 4 to the n is the growth, 3 to the n is the less important part, so we throw it away. And you can check. This is a smaller denominator because you'll see over here we've added something. Now, can I just throw something away here? And the answer is no. See, because if I just throw something away, it'll be a smaller numerator, and then all bets are off. So if I can't throw it away, what can I do? And the answer is bump it up. Well, what does that mean? Well, see, 2 to the n is going to be below 3 to the n. So what we're going to do is we're going to take the 2 to the n and we're going to promote it to be 3 to the n, and the 3 to the n we're just going to leave as is. In other words, we're going to raise all the other terms up to the largest term. And we're okay to do that. So you can check. We're on track. We have a larger numerator, smaller denominator. The result is this term on the right is larger than the term in the middle. So that becomes 2 times 3/4 to the n. Because this is really 2 times 3 to the n. See, that's why the bumping up works so well. When you bump it up, then you really can say, oh, look, addition is really simple. And what else we know? We know that the sum, 0 to infinity, of 2 times 3/4 to the n converges. In fact, if we wanted to, we can even say explicitly that it converges to something like 8. Not that we want to, but we could, but we're not going to. All right. So the conclusion is that by the comparison test, the original sum, so that's the sum from 0 to infinity, of 2 to the n plus 3 to the n, divide that by 3 to the n plus 4 to the n, also converges. And so, lo and behold, the answer is another example of something which converges. I don't know if we've been keeping track, but there's a lot of converging on this quiz. Well, to be honest with you, oftentimes when something diverges, it oftentimes diverges for like a really simple reason. And the really simple reason is because the terms get large. It's possible to have something which diverges where the terms get small, but it's trickier. So, all right, number 7. Determine whether the sum from 1 to infinity of n over 2 to the n plus 1 to the nth converges. All right. Well, what can we do? What can we do? Well, there's a couple things we can do. Now, one thing we can do is think about, all right, n over 2 to the n plus 1. This number right here, n over 2 to the n plus 1, you'll notice if you got rid of that plus 1, it's really simple. It'd just be a half. Well, how does this compare to a half? Well, it turns out that it's less than a half. Now, how can you see that? Well, if you think about removing the plus 1, that's going to make a larger number, right? Because you're going to have a smaller denominator. Smaller denominator, larger number. And now, if you take both sides to the nth power, then you still have that inequality, and of course this is certainly bigger than or equal to 0. All right, now what can you say? Well, the sum from n equals 1 to infinity, 1/2 to the n, converges. And why do we know that? It's geometric. So, by the comparison test, we can also conclude that the sum from 1 to infinity of n over 2n plus 1 to the n converges. All right, well that was kind of too easy. Let's do it again. Okay, this problem is so nice, we're going to do it twice. Now, how can we do it twice? Well, notice something. this thing right here, the nth power. So when you see something to the nth power, you can think of a root test. Right? Well, what does the root test says? Well, it says take a limit as n goes to infinity of an to the 1 over n. Now, when we have an expression where everything is to the nth power, and that's, for an example, this problem has that, then n to the 1 over n, see something to the nth to the 1 over nth, what happens with these? Well, they combine together. And what do you end up with? Well, we end up with just n over 2n plus 1 to the 1th power, which we just write as n over 2n plus 1. Now, what's this? Well, this is polynomial over polynomial at the same degree. It's easy to read off the leading coefficients. It's a half. Now, what's true about a half? Lots of stuff. Well, what's true about a half that we care about? Well, when you're doing a root test, the key is, how do you compare to 1? And in this case, we compare very favorably to 1. We're below 1. So, by the root test, we see that we converge, because the limit of a sub n to the 1 over n is below 1. All right, so good. Now, you might notice that in both tests we got the same answer. When it's the case that more than one test can apply, it will always be consistent. You'll never get a sum where you say, oh, by the ratio test it diverges, but by the limit comparison test it converges. No. It's always going to be consistent. And if you are getting more than one answer about converging and diverging, then what that means is you made a mistake in one of your tests. So, do we care what test you use? Generally speaking, no. You should use what test you feel comfortable using. Occasionally we'll say specifically, use such and such a test, but we'll avoid that for the most part. So, all right. So anyways, that's the answer for number 7, which means we're getting closer to the end. Number 8. Determine whether the sum from 1 to infinity of arctangent of n to the n over 2 to the n converges. Now we've got to actually do this very similar to the way that we did our last problem. In fact, we could do this 2 different ways. We could do this by comparison, or we could do this by root test. Any preference? No preference? Okay, all right. We'll just do it by a root test, because I think it's good to get the hang of that. So we'll apply the root test. And the root test, by the way, is going to be one of our most important tests. So I want you to be really comfortable with applying the root test. So what do we have? Well, we're going to get the following. So we're going to take the limit as n goes to infinity of arctangent of n to the nth power, divide that by 2 to the n, and all that is to the 1 over nth power. Now, this becomes the limit as n goes to infinity, arctangent of n to the 1 over n. What happens? Well, what happens is it becomes arctangent of n to the 1. Downstairs, 2 to the n to the 1 over n becomes 2. So now we have to say, well, what happens to arctangent of n as we let n go to infinity? Well, if you know arctangent, and who doesn't know arctangent? I mean, that's kind of a silly question. Everybody loves arctangent. It's like the coolest curve ever. You know, if, well, I'm not a highly religious person, but I could imagine that, you know, if there were somebody who was religious, they would say, you know, and on the 8th day, God created arctangent. Because it's just such a beautiful curve. You know, he needed to take a day off before he could do it, though. All right, so if you know arctangent, what happens is it has asymptotes. So as you head off towards infinity, what you get is that arctangent approaches pi over 2. So this becomes pi over 2, also known as pi over 4. Now, we don't need to know too much about pi over 4. Because we're doing a root test, the only thing we need to know is how does pi over 4 compare to 1? And the answer is, it's below 1. Pi is 3.1415, just remember the chant. Cosine, secant, tangent, sine, 3.14159. Yay! Okay, good. All right, so by the root test, because we took the limit of a sub n to the 1 over n, and we found that it was below 1, we can say that the sum converges. All right, good. Converges. And there we go. All right. Now we're getting close. We're in our home stretch. Number 9. Determine whether the sum from 1 to infinity of 3 to the n over n to the 1000 e to the n converges. Well, so okay, like n equals 1, that's 3 over e. That's not a big number, it's like 1 point something something. N equals 2, that's 9. E squared, I don't know, it's a smallish-ish number, 8 point something. And 2 to the 1000, oh, huge. In fact, that's going to be massive. N equals 1, 2, 3, 4, 5, 6, 7, up to 1000. It's ginormously huge. You plug it into a calculator, and your calculator is going to say it's 0.0000000. The terms are unbelievably small at the start. But wait a second, we're not going to be tempted by saying, hey, it's small at the start, because questions about convergence, we don't care about the start, we care about the end. Because there's a lot of space up there at infinity, and a lot of things can happen. So let's not be tempted. Okay, so what test should we use? Well, I would say our default test should be a root test. If you have things involving addition and subtraction, use the limit comparison test first, clean that up. Then the next test should be a root test, unless you have a good reason to not use a root test. And you might be wondering, what's a good reason? Wait a second, we've got number 10, so hold on. All right, so let's do our root test. So we're thinking of this as our a sub n. So we're going to take our limit as n goes to infinity of a sub n to the 1 over n. So this is our limit as n goes to infinity of 3 to the n over n to the 1000 e to the n to the 1 over n power. All right, 3 to the n to the 1 over n. Well, that's easy. Now notice that one of the things you can do when you have something to the 1 over n power is you can do 1 over n to each term. So 1 over n here, 1 over n there, 1 over n there. And we can do it because it's all multiplication. That's why you want to get rid of addition. Limit comparison, get rid of addition. So upstairs is 3. Downstairs we actually have something easy, that's e. And then you have n to the 1000 to the 1 over n. So that's going to be the tricky part. But not so bad, right? Because here's something cool you can do. And this is a really useful fact to remember. So if I have n raised to the a raised to the b, that's n to the a times b. Well, that's not so surprising. That's how exponents work. But here's the cool fact. I can make it n to the b to the a. In other words, I can swap the order. So that becomes 3. Divide that by n to the 1 over n to the 1000 times e. Now, why do we care about that? Well, because we're going to write down a cool fact. So, over here, cool fact. Now, how do I know it's a cool fact? Because it says it right there. Cool. So it must be true. All right, so what's our cool fact? It's that the limit as n goes to infinity of n to the 1 over n. what does that become? N to the 1 over n becomes 1. That's a really useful fact. In fact, I'd say it's very cool. Something you might want to know. So this part inside is going to 1. So what does that tell us? Well, if I take 1 to the 1,000, how does that behave? The answer is, whoops, you don't need to do a limit anymore. It just goes to 1. So we end up with 3 over e. Now, again, we're doing a root test. We don't need to know a lot about 3 over e. The only thing we need to know is how does it compare to 1. So we think, what can we say about this value for e? Well, e, it's sometimes, I think people might call it Euler's number. Is there a chant for e? Well, maybe you can do something like this. Come on, exponentiate 2.71828. Oh yeah, that's right. Good. So that's what e looks like at the start. 2.71828. So if I take 3, divide by 2.7 something, is that bigger than 1 or less than 1? It is bigger than 1, right? Because it's 3 divided by something smaller than 3. So, a root test, we got something which is bigger than 1. What's the conclusion? So, we can say, by the root test, since our limit, our limit as n goes to infinity of an to the 1 over n is above 1, the sum, do you remember what it is? It diverges. And really what happens is what's going to happen in the long run. We said at the first couple of terms, it's very, very tiny, and it's absolutely true what we said. You look at the first million terms, look at the first billion terms really, and it's going to be microscopic. You probably won't even notice it. But you see, infinity is very patient. It can wait. And it can wait a long time because, well, infinity, there's a lot of space there. And so don't be tempted by what happens at the start. It's what happens at the end that's the interesting stuff. All right, so the sum diverges. Good. Bringing us to our last problem. Well, for now, don't worry. We got a few more quiz problems left for the next couple of weeks. So, determine whether the sum from 1 to infinity, 3n factorial divided by 7 to the n times n factorial times 2n factorial converges. Does it converge? Now, remember our sort of philosophy. I think this is a good strategy in general. If there's any things being added or subtracted, use limit comparison, get rid of that. Then you use a root test unless there's a good reason not to. Now I said, unless there's a good reason not to, but what's a good reason not to? And the answer is, and this is not the only answer, but if you ever see those exclamation marks, it's not like we're going around saying 3n on the top. No, 3n factorial, right? It's not just that we're very excited about that 3n. It represents something. And so when we see this, we say, aha, factorials mean in something in particular, it means that we're going to use the ratio test. Okay, so now we have our stratagem. We're going ratio test. We're committed. So this is our a sub n. Now, let's talk about the ratio test for a second, because it's a good test. We're going to take the limit as n goes to infinity of a sub n plus 1 over a sub n. And that's where the name ratio test comes into play. You know, we're dividing the next term by the current term. So, there's a couple of hard things to do here, but if you're aware of them and you think about them, then they don't become so hard. The first hard thing is, how do I get the next term? The answer is, I come here and everywhere where I see an n, I'm going to put an n plus 1. And this is a case where parentheses are your friend. You want to hang out with parentheses and say, hey, parentheses, let's work together. So 3, and everywhere I see an n, I'm going to put a parenthesis n plus 1. And I'm going to do that because I want to make sure that I get the right term. See, if I just wrote 3n plus 1 factorial, that is not the same as writing 3n plus 1 factorial. These are not the same. So you can tell they're not the same because I wrote not the same. Why not? Well, this is really 3n plus 3 factorial. So that's why you want to make sure you're extra generous with your parentheses. All right, downstairs, well, we have 7 to the n plus 1, and I'll go ahead and put parentheses here, n plus 1 factorial, and then we have 2 times n plus 1 factorial. Okay, that's our an plus 1. To get an, we just flip everything. 7 to the n factorial, 2n factorial, 3n factorial. All right. So this is our limit. N goes to infinity. And we're just going to clean up a little bit. So again, multiply through. So 3n plus 3 factorial. And I'm going to put underneath what corresponds. So there's a 3n factorial. And then let's see, our next term here. Well, there's a 7 to the n. Downstairs, 7 to the n plus 1. N factorial. Downstairs, n plus 1 factorial. Then upstairs, we have a 2n factorial. Downstairs, a 2n plus 2 factorial. All right, cool. Now, here's why we're going to do the ratio test. Is because when you see things with factorials, when you're just a little bit off, see the 2n and 2n plus 2? That says you can simplify that. And the way you do that is you make the following observation. Let's suppose I look at 2n plus 2 factorial. See, what 2n plus 2 factorial looks like is it's 2n plus 2 times 2n plus 1 times 2n, and then you keep going. But this last part is simply 2n factorial. So in other words, what you can do is you can pull off the first couple of terms. In this case, pull off the first 2 terms, and then what you're left with is something that's much simpler. So it's that ability to pull off factorials. That's why we like to use our ratio test in this setting. All right, so we're going to do that for our pieces here. So limit n goes to infinity on our first term, 3n plus 3, 3n plus 2, 3n plus 1. And then after that, we're 3n factorial, and so we'll stop because we have a 3n factorial downstairs. Now the next term, well, it's not a factorial, but we have 7 to the n plus 1. So that would just leave us with a 1/7 downstairs because we can knock off powers of n. So we're just basically doing this a pew, pew. See? Now, if it helps, you can make the pew, pew sound, but you don't have to. It's not a requirement. Okay, the next term, well, the n plus 1 is bigger, so I leave the top alone. Downstairs, I pull off an n plus 1, and now I'm good to go. Again, the next term, the denominator is the bigger term, so leave the top alone, pull off the first 2 terms, and then what's left is 2n factorial downstairs. Okay, more of our pew pew action. The 3n factorial, pew pew, n factorials, pew pew, 2n factorials. Wow, we pew pew the heck out of that. Excuse my language. Sometimes I get excited when I'm doing a calculus problem. I get a little bit salty with my language. All right, now what happens next? Well, what happens is everything that's left is polynomial. So let's take a look at this polynomial. And when I'm doing polynomials, all I care about are my leading coefficients. So highest powers. So upstairs, the highest powers will come from multiplying the biggest terms. So 3n times 3n times 3n. So it'll be 27n cubed plus lower order terms. So I'll put dot, dot, dot. And I'm going to use that to mean lower order terms as I look at this. Downstairs, we're going to have 7 times n times 2n times 2n. So 7 times 2 times 2 makes 28, right? 7 times 4. But again, n cubed. And then there's lower order terms, which I don't care about. Well, what does that become? The answer is, you just focus on the coefficients for the highest terms. So 27 over 28. Now, this is close, really close. It's almost like they wanted it to be really close. Is that below 1 or is it above 1? It's below 1. So, by the ratio test, since our limit as n goes to infinity, an plus 1 over an is below 1, the sum, what's our conclusion? Converges. That's right. Good. So this is I'll put it up here. This is a converges sum. Now this is a case where it wasn't clear. It was really close. You wouldn't be totally sure before you did the work whether it converges or diverges. But that's why we do the work. We do the work because the more that we do, the better that we get. And don't worry, we get a chance to do a little bit more work in the next couple weeks. So that's it for this time. All right, my friends, stay healthy, and we'll see you next time. Bye.